So good day everyone. This is the next topic for rectilinear motion of particles, that is motion of several particles. And the main reference for this topic is from Hubeler, that is the Engineering Mechanics Dynamics. I also include some content from Beer's book. So for the motion of several particles, what you will learn here is that what I discussed before, especially on the rectilinear kinematics for continuous motion and erratic motion, we describe a motion only for one particle. And for this one, what we consider or what we describe is the motion of two particles now. So when several particles move independently along the same line, independent equations of motion can be written for each particle. So whenever possible, time should be recorded from the same initial instant for all particles, and displacement should be measured from the same origin and in the same direction. So in other words, a single clock and a single measuring tape should be used. So for motion of several particles, we have actually two topics to consider. The first one, I will discuss about relative motion of two particles, and later is the absolute dependent motion analysis of two particles. For relative motion of two particles, let us consider two particles A and B as shown here in this figure. So we have particle A and particle B moving along a same straight line. So that is moving in a horizontal um, line or a coordinate horizontal axis. And if the position coordinates xa and xb are measured from the same origin, the difference xb minus xa defines the relative position coordinate of b with respect to a and is denoted by xb over a. So we write xb over a equal xb minus xa, or the position of particle b is equal to the position of a plus the relative position of b with respect to a. So when we talk about the relative position, if it is written in this way, it means that the particle b is with respect to a. But if it is the opposite, a over b, so it is the relative position of a with respect to b. So regardless of the positions of a and b with respect to the origin, a positive sign for xb over a means that b is to the right of a, and a negative sign means that b is to the left of a. So from the position, we consider also the rate of change of the relative position of b with respect to a, and it is known as the relative velocity of b with respect to a and is denoted by vb over a. And when we differentiate the previous equation, we write vb over a, which is equal to vb minus va, or the velocity of particle b is equal to the velocity of a plus the relative velocity of b with respect to a. So positive sign for vb over a means that b is observed from a to move in the positive direction, and a negative sign means that it is observed to move in the negative direction. Likewise, if we determine the rate of change of vb over a, that is known as the relative acceleration of b with respect to a, and is denoted by ab over a. So differentiating the above equation, we obtain the relative acceleration of B with respect to A is equal to the acceleration of particle B minus the acceleration of A, or the acceleration of particle B is equal to the acceleration of A plus the relative acceleration of B with respect to A. So just a procedure for analysis: when you encounter a problem that has relative um, motion, or that is relative motion of two particles, first is for applying equations of relative motion for independent motions of any two particles moving along the same straight line. You begin your solution by listing the given information and sketching the system and selecting the origin and the positive direction of the coordinate axis. It is always advantageous to have a visual representation of problems of this type. Next is you write the equations that describe the motion of the various particles, as well as those that describe how these motions are related, and define the initial conditions, that is specify the state of the system corresponding to the time that is equal to 0. And this is especially important if the motions of the particles begin at different times. So in such cases, either of the two approaches can be used. So we have the first one. We let t is equal to 0 be the time when the last particle begins to move. You must then determine the initial position xo and the initial velocity vo to each of the other particles. And for the second approach, let t is equal to 0 be the time when the first particle begins to move, and you must then, in each of the equations describing the motion of another particle, replace t with t minus to, where to is the time at which that specific particle begins to move. And it is important to recognize that the equations obtained in this way are valid only for t is greater than or equal to to. So later I will show you one example problem for the relative motion of two particles.